So here are the pages that I'm going to cover right here. It's not too many things, just some operational things for op amps. And first what we'll do, we'll go over a few things that we went over last time. So again, here's your, how your memory works. Okay, so it's really important for you guys to understand that to, make your education go a little more smoothly by being able to put things into your memory and understand those kind of things. So again, what we talked about last time are the decay of your memory curves right here. So depending on how many times you review, what days you review them on, your memory follows a different exponential decay, right? And it asymptotes, okay? But as you can see here, the more times you review, it'll asymptote to a higher value, which can be above 90%. Here's a slide that reviews basically lecture 1 material. Okay, so we've seen different abstractions of types of amplifiers. So here's like a stereo amplifier that could be looked at as like this, where it receives some type of voltage input. In this case, it's an antenna. And it has a load output. In this case, it's the speakers. And lots of things are going on in here where it's amplifying that signal that's coming through. It's doing some processing too, right? But the whole goal is to take this signal, filter it out, and get the signal that you want, amplify it, and push it through to your load, which is the speakers. And here's another abstraction of that where you can take this thing right here, this in a box, and say, well, here's just my amplifier. The antenna is supplying some type of voltage, really small, but it has some resistance to that antenna, right? And here's the speaker, which can be lumped into a resistor. And this part right here can be abstracted to something more simplified, where you can model it like this, where it has some type of resistance coming in, some type of resistance that you can see if you're looking at it from this side, and you're amplifying it right here. And of course, inside this stuff, you're really having lots of components. It's not just a very simple type of thing. It's very complicated in there. Lots of different components. And of course, this right here is an amplifier that's just like this, but it's more of a basic model. And that's what we are dealing with in this chapter, are these op amps that look like that. Okay. All of these things right here are forms of these 2-port networks, right? You have, your input port, your output port, that can be described like this. And because of that, you can get your G parameters, and you get your G parameters like this. You take the ratio and you assign something to 0. Like if the current is 0, that means there's no current coming in right here. If the voltage is 0, that means that you put a wire right here and you short circuit it. We also looked at decibels. Okay, so if your power, right, you have this 10 log of the ratio of output to input. If it's voltage or current, it's 20 log. And then we saw that with these things, they really mean the same thing, right? It's just that when you write it out, they look different because you have to say this right here is the gain in terms of power. Here's the gain in terms of voltage or current. So you have to say which one. Once you say which one, then these make sense, right? Because one has a 20 out here because that 2 came out to the front right here, and that's why it became 20. But then it's described like this. If it stays in the power domain, then it's a 10 right there. Got 2 stays in here because power signals are squared, and so it looks like that, right? But still, it's the same type of gain, same value. But in decibels, it looks different. But the actual gain is exactly the same, regardless if you do 60 or 30 for those things. Okay, and we also did a review what root mean squared means, where it's the root. That means the square root, the mean, and then the square of whatever signal you're looking at. So that's basically lecture 1. For lecture 2, we look at the voltage transfer characteristic, okay, of these op amps. So basically, they have these limits right here and these are the voltages that are being supplied to power the op amp. And so your input is coming in through here, and here's a good way to describe that, because the slope right here, the slope of this is the gain, rise over run, okay? So it goes out like this, and it comes out this way. So there's some amplification that's happening here. Here's the offset that we looked at right there. And we also saw the case where if this amplitude was much larger than this little dash, this vertical dash line, maybe it went from right here and then was clipped off right here. And if that happened, that means that these peaks right here would be clipped off. These wouldn't, but these would be. And that's where you get your distortion. And we also describe distortion as harmonics, because any signal can be described with a Fourier type of series, right? And a Fourier series is just taking, breaking components up in terms of harmonics. And so harmonics just means that here's your fundamental frequency. Each additional component is a multiple of that. So it's 2 omega, 3 omega, 4 omega on out. And they each have a coefficient in front, right, that magnifies its component here. And that's also called the spectrum, right? So you might see spectra where here's the magnitude of the spectra, but it's at that frequency, that particular harmonic. So you have a DC component, your desired signal, and all these interferers right here that's interfering with your nice signal that you really want. You can describe that with a percent THD, total harmonic distortion, okay? And 10% times the square root of these things squared, so from 2 on, so you're just squaring all those, divided by that one, right here. We also looked at a differential amplifier. So we described it in this form right here. And these quantities on the end is if you're looking at an ideal differential amp. Okay, it goes from this to this, this to that. And we also looked at an ideal operational amplifier, right? And we found out that the voltages across the inputs, okay, that's supposed to be equal signs. I'll change that. And also the resistance of your of this right here is RID, your input resistor. That's infinite. So that means that there's no current going in or out of this. Okay. And to determine this V out, you have to use KCL, KVL. Those are 2 laws for electronics. I think everything revolves around that, electronics, right? And if it's inverting op amp, then your amplitude is less than 0. Your gain is less than 0. And if it's not inverting op amp, then the gain is greater than 0. Okay. So here are the concepts for today. So we'll cover transimpedance amplifier, which is a current to voltage converter. We'll look at non-inverting amplifiers, unity gain buffers, voltage followers, summing amplifiers, difference amplifier, and we'll start to touch on frequency-dependent feedback. That's all the pages we're going to cover today. So before I continue, are there any questions about Lecture 1, Lecture 2 material before we go on? Anything? Okay. So transimpedance amplifier. Okay, so this is a current to voltage converter, and it looks like this. Okay, and so we'll look at some more of these, and then we'll do it by hand on the whiteboard. But just to go over one, you can look at this in most cases as an ideal op amp. If it's ideal, that means these currents, I negative and I plus, going into the non-inverting and inverting inputs, those are all 0. Okay, so if you're going to do KCL, you got to watch out for that. That's 0, and that's also 0. The voltages are equal. So the inverting and non-inverting, these are equal. And so here, I have to ask the book author about that, Jaeger, but I think this is true. That even though these are equal, the way to think about this is that the voltage here goes to that one. Okay? So the voltage that's coming into the non-inverting input, that voltage is copied here, not the other way around. Okay? But I need to double check that. But like when I'm doing the math, it works out that way. And also there's going to be some other circuitry that you'll have around this, and then if that's true, it makes that analysis a whole lot, well, it makes it make more sense, I guess. But so I think that's the case, that there's some directionality in this equal sign. Okay? And also that's why I said this, that this V negative equals whatever that is. I didn't say V plus equals V minus. Mathematically, it means the same thing, but again, I want to check that. So hopefully I'll have the answer by Monday. I'll tell you guys. Okay, but so to analyze this thing, if we're trying to find, the gain of this going from from input to output, first you do your KCL, right? So the sum of the voltages entering or exiting this has to equal to 0. This is just conservation of matter, right? So you add them all up, that has to equal 0. So in this equation, you find out where all these i's are. So I1, right here, well, that's the negative of II. That the current's coming in here like that. Here's the direction of I1. It's the same magnitude, but it's pointing the opposite direction. I could have these arrows go into the node. That's fine. If they go into the node, it's just that all these are negative. It's the same equation. I can even have some going in and some going out. I just have to define in my equation, well, are the ones going in negative, or are they positive? Are the ones going out positive or negative? So for example, if I had I2 and that arrow was pointing into the node instead of out of the node like it is, and I define all things going out as positive, that means that would be positive 1. The I2, if that arrow was going down into the node, I would call that negative I2, and that positive I negative. Okay, so what I'm trying to say is you always need a picture to go with your analysis. If you don't have a picture, you can't say what direction the currents or the voltages are going. So you need that picture. Because if you get a value of I1 and it says 5 amps, what direction is it going? You have no idea until you see the picture. And in fact, if someone else, your friend, did the same analysis, except he or she, used different arrow directions, then they would still get the same result, except if they had negative 5 amps and you had positive 5 amps, you guys can still have the right answer if you go back and look at your diagram. Okay? So as long as the current's going the same direction according to your diagram, then you're fine. So always have a diagram with these things. Like you shouldn't ever just have an analysis about the diagram. It wouldn't make sense. Okay, but anyways, that's what this is. For I2, that's the current going this direction. And for using Ohm's law, remember that the direction of the current flow that you're assuming as positive sense goes from the is the voltage that is going in at minus the voltage that's going out at. Okay, so it's not final minus initial, like you're typically, what delta usually is. It's the opposite of that. Okay, if this arrow was going the opposite direction, going into that node, then I would have V0 here be negative there. Okay, so you got to be really careful about your directionality of your voltages. Now, if you found out that I2 was negative, it has some negative value, then you look at your picture and say, oh, if it was positive, it would be going this direction. But if my current was negative, if my current is negative, I now know the current is actually going this direction against my positive sense. The current going into the ideal op amp right here is going to be 0 because remember there's infinite resistance between here and there. Again, that's ideal. Okay, case it's not really infinite. It's very, very large compared to everything else. And also, this right here, this voltage right here gets whatever that voltage is, and that voltage happens to be ground. It could be something else. It could be a voltage here. It could be attached to some circuit components, okay? But whatever it is, it gets copied there. In this case, it's ground. Okay? So I have all these components. I take this, plug it in here. Well, I just substitute everything in here, and this is what I get out. This is the only unknown I'm looking for. Okay? But plugging all these things in to this equation, this KCL equation, I get this. And as you can see, it's negative. Okay? And so you could think of this as an inverter, right? It's taking some signal that could be positive, it could be a positive current sense, right? But it's negating it, okay? But that's the voltage coming out. And that's called a transimpedance amplifier, or TIA. Okay, so any questions about this kind of thing here? Okay, good. All right, so now let's look at the gain. Okay, so this is what we got last time for the answer. Okay, so the gain is just the output over the input, right? So the output VO over the input II. Well, the output was this. The input is this right here. The two I's cancel out, and we get this. And if we want to put this, since it's voltage, it's not power. If it's power, this would be 10. If it's voltage, we put 20 log or whatever that is, and that's in units of dB. Okay. Okay, so let's look at the inverting amplifier. So let's go through this, and we'll figure it all out. What these things are. We'll determine the gain of this. We'll determine why it is an inverting amplifier. We'll look at the input resistance seen from this side over here. We'll look at the output resistance as seen from the output. Okay, and try to characterize this whole thing. Okay, so so let's start by looking at the gain, AV. Okay, so let's say you're given this, and then you got to figure out output over input. So what you can do is do KVL or KCL, whichever one is fine. If you're going to do KCL, you probably want to do it right there. Okay. If you're going to do KVL, you have to look for some loops here. So here's one loop that goes this direction and around this way. This loop makes sense, because you clearly see the voltage, across here. You're going to have a voltage drop here. The voltage across here is going to be 0, so it's a 0 drop. So that's one path. Now, this could be a path around this direction, right here. And I should have stated this, but this is like with reference to ground. So if there's like a ground node here, then you can possibly go around this direction to the ground, like that. You probably wouldn't want to do a path that goes around like this and then through here. And the reason why is because we're modeling this as an ideal op amp, and you don't really know what's going on in here. Okay, it's idealistic. So I wouldn't recommend going that path. But go through paths where you know what's going on. Okay, so let's do KCL right here. Okay, so in that case, let me just draw redraw the circuit here, so I'll have it. So can you guys see this in the back? Is this large enough for you guys? Can anyone not see this? Okay. Okay, so we have this feedback resistance right here, and oh, forgot about this resistor. Here goes R1 right here, plus and minus. Okay, that's all we have. Bn. Okay, so let's do KCL right here. Okay, so we have these currents. Let's define them leaving that node as being positive. So what's this current going to be right here? Going into the op amp.
0.
Yeah, that's going to be 0, because that is our ideal op amp. That's 0. Okay, so let's call this I negative, I feedback loop, and I let's call it I1. Okay, so I negative is going to be 0. IF, what's IF going to be in terms of Ohm's law?
V negative minus VO RF.
Yeah, V negative minus VO over feedback resistance. Yeah. Now, again, if I had the current going into that node, going in that direction, I would flip these around. It would be the current going this direction, so it would be VO, that voltage, minus that voltage, which is V negative over R. And this one right here, I1, what's that in terms of Ohm's law? This current right here. Yeah, V negative, because so it's going in on this side is V negative, right here. What's the voltage on that side? Yep, VI over R1. There you go. Now remember, KCL says that these created are destroyed, so all the current right here has to equal 0 if you sum it all up. Okay, that's what KCL says. All right. Now, another thing for an op amp is this right here is this V negative equals whatever V positive is. In this case, what's our V positive?
0.
Yeah, that's grounded. So that voltage right here is 0. Yeah, so V minus equals 0 because it's grounded. Okay, so so let's just plug our things in here. For V1, we're going to have a 0 here, so minus VI over R1. For IF, that's going to be 0, so that's going to be negative V out over RF. And this term right here is going to be 0, so that has to equal 0. Now this is kind of nice because we're looking for the gain, we are looking for the ratio of output over input. So we can find it from this, right? So for this equation right here, we can just take this term, put it on that side, or we're actually, let's take this term, put it on the other side. So negative VO over RF, that equals VI over R1. And then take these two things and put it on this side. So V out equals negative RF over R1 times VI. Okay, so here's the what V out is. Okay, and of course we're looking for the gain, and that's just V out over V in. So the gain A is equal to V out over V in, and that's going to be negative RF over R1. Okay. And so the next question is why is it inverting amplifier? So why is that? Well, look what's happening here. Whatever VI is being negated, right, with a negative. So if that's positive, well, we already know the resistors are going to be positive. They're just passive, right? Now, let's just say RF is equal to R1. Let's say they're both, 10 kiloohms. That's going to be 1. So whatever VI is going to be negated, and that's going to be V out. Okay, so this is called an inverting amplifier because of that negative. You can also think of it as being 180 degrees out of phase. That's another way you're looking at it too. Okay, now let's look at the input resistance, Rn. So that's looking at it this direction. Okay, so if you look at that, like if this was like a black box here, like all around here was a black box, and then you don't know what's inside, and then you're going to apply a voltage source to see, how much current is being generated from that voltage source. That ratio is going to tell you what the resistance is, right? I mean, because just for simple Ohm's law, V equals IR, your input resistance is just going to be the ratio of voltage over current. So you either apply some voltage and measure some current, or you apply some current and measure voltage. You take that ratio, that's going to be your resistance that you see looking into that black box. Same with the output. You apply a current or voltage on this side and see what kind of ratio you get, and that would be your output resistance that you would see from wherever you're connecting it to. Okay, so what's happening? Like if I apply this voltage right here, current's going to go through here, but what voltage is right there? 0. So that looks like this. If you think about it, like it's just going to ground directly. It looks just like that. Okay? So the input resistance just looks like R1. That's what it looks like from the outside. Clearly no current is going down this direction. Is doing this other stuff, and then is going into the op amp. So but it looks like this from the outside. What about this way? If we look in this way, and I apply some current going in this direction, or some or high voltage. Okay, so if I apply current, what is it going to look like? Like what resistance do you think you would see?
Mostly RF.
RF? So that would be true if you didn't have this.
Ground, sorry.
Huh?
It was reference to ground.
Yeah. Yeah, so this is kind of weird. Your current going in here, some of it's going to go through RF, going to go through R1, and then going to go through downhill through that voltage source, because you're forcing current through there. But also, some current's going to go into that op amp. And remember, this model of this op amp is ideal. Okay? So, for these ideal op amps, remember we talked about yesterday, that current, it could be anything. It could come out of that node and go into that node. And it appears, the resistance is so small, it appears as almost being 0. Okay, so when your current is going through here, it can choose 2 paths, through RF and R1, or it can go through this path, which is nearly 0. So if you have current going like that, where you have your current source, and that's going to go through here, and it can have two paths to ground. One, you're going through a couple of resistors before it goes to ground, and another path which has nearly no resistance and going to ground. What path is it going to choose mostly? Yeah, it's going to choose this one, right? Lib is going to go that way, but that's if it has a little bit of resistance. But if this is assumed to have no resistance, it's like you're short-circuiting it. So all your current is going to go through that path. Okay, so from the outside, it looks like that black box has no resistance. Looking at it from the outside. Okay. Questions? Yeah.
So would Rn just be R1 and R out would just be pretty much 0? Same as
Yeah.
last ones?
Yeah. That's great. Okay, so let's look at this right here. Okay, so this is a non-inverting amplifier. Okay, wait, do we answer our questions? Yeah. Okay, so we'll find out why it's called a non-inverting amplifier. Probably guessed already, but so the first question is, can voltage division be used at this node right here? Right. Remember, voltage division is like you're like looking at a node for the voltage, and that voltage is what resistance remains over the total resistance multiplied by the voltage that it started from. Okay? So can you use voltage division right here? You see some thing connected to it. What do you guys think? Let me ask you this. If you didn't have this thing connected to it, you just have like a little test probe that didn't really disturb your system very much, and you code for voltage, that's fine. But having something connected right here is a problem, because you're like thinking, hey, this current going through here, that voltage that I get through here depends on all this current going straight through and continuing on that way. If some of that current goes here, I get lower amount of current going through there. That's going to change my value of voltage. It's not going to be, an accurate representation of voltage. But how much current is leaving out of here going this direction? 0, right? Remember, no current going in or out of this op amp. So you can use voltage division. Okay? If this was not 0 current coming out of there, and I had something else connected to it like a resistor, and it went to ground, I cannot use voltage division right here on that. It had like a power source or current. You cannot do that. You only do that if there's no current going in or out. Okay, so we can use that here. Okay, so let's look at the voltage gain. It's a terrible eraser. Okay, so I'm not going to draw the circuit, I'll just draw the equations. So for the voltage division, V1 equals R that remains, which is R1, over the sum of all the resistances in that path, plus V0. Okay? And this voltage right here is what?
0.
The voltage?
Yeah.
Yeah. Over here. Oh, here's a good example of why I think this voltage gets copied here. It's because of that. You see what I'm talking about? I'm not gonna, well, I'm not sure. Okay, anyway. So this voltage, this voltage right here gets whatever that voltage is. So that's VI. Okay? Which is kind of weird. So I'm basically telling this voltage to be a certain thing. So this voltage V1 is really forced to be VI. Okay? Right? So if I want to look at the gain, well, I already have an equation that has VI and V out. That's all I need. I just need that equation. So V out over Vn is going to be, I just take this and flip it. And I can just reduce it to be something like this. Okay? That's the gain. So is this a non-verting or inverting? Why? Why is it non-inverting?
It's not changing the sign of the
Yeah, there's no sign change. You know, here's like the amplitude that, well, if I wrote like this, V out equals this thing right here. I take this input, whatever the input is, I multiply it by this factor, and that tells what the output is. There's no sign change. If the input's positive, output's going to be positive. It's going to be magnified or reduced, but no sign change. Okay? Now, is there anything interesting here? Again, the current going through here, where's this current coming from? It's all coming from inside of here. I mean, assuming it's nothing connected. If nothing, if this is like this dangling here, there's nothing connected, all this current through here is going through there just like that. Unless this is ground. If I want my current to go up that way, what does this have to be? It has to be negative. So if this voltage source right here happened to be like negative 10 volts, that's negative 10 volts, that's negative 10 volts, that's negative 10 volts. If that's ground, this is a high voltage, that's a low voltage. The current's going to go this direction, going to go into that op amp. Okay, so this is a unity gain buffer. Oh, any questions about this before we move on?
So you said you can't use KCL on this, on certain parts of it?
Oh, on this?
Yeah.
You can use KCL.
I guess I was confused at the beginning when you were talking about this.
Oh, that was a voltage division.
Okay.
Yeah. I chose to use voltage division on that. And I told you like when you can and cannot use voltage division. And like if you have current coming off of it, you can't use it.
Okay.
Yeah. But yeah, you can use KCL on anything.
Yeah.
Because those are like the laws of KCL, conservation of matter, KVL, conservation of energy. They apply everywhere. So this right here, this is a unity gain buffer. Okay. So well, we could just, look at this right here. Okay, before we do the gain, you can just see this right here, what was happening. If this was a black box, right, and you apply some voltage here, how much current is going to go through this voltage source? 0. Right? Our original equation. Well, if your ratio of voltage over current, if current is 0, anything over 0 is going to be infinite. So your resistance is infinite going into that op amp. You got an infinite voltage. On the other side, if you're looking at an out, If you have current going in here, you know no current's going to go this direction because of this. Can't go in there. All your current's going to go straight on through, and it's so small, it appears to be zero. So zero resistance looking at it from the output. Okay? The voltage gain here. Well, we just look at this. This is the non-inverting node. So this voltage VI, that's the voltage right here. It gets copied to here. This voltage here gets copied to here because there's no drop. There's no resistor. So that voltage is right here. I don't know what the current is, but I know what the voltage is. The current can be anything. It doesn't matter. But the voltage is, that's the voltage. So it's weird. This device just takes that voltage and copies it over here. So, so how is it useful? Well, why would you want to use something like that?
It sinks no current. Beam smashing or.
Yeah, it doesn't take anything away from what you're measuring. Like, what kind of thing would you use it for?
You were measuring a sensor that couldn't source any current.
Yeah, like a very small sensor, and you don't want it to disturb it. If you're, if you like get into bioengineering, if you're a grad student and you're probing around trying to understand the signals that go from your brain to your extremities, you would want to say, okay, well, here's my probe here. I'm going to probe around in a brain to figure out what the voltage is. You don't want to suck current away, right? That's going to destroy your whole experiment. You just want to probe for the voltage. That's it. Just probe what the voltage is. You know, there's a voltage difference between me and you. Like, let's say I'm at, 10 volts and you're at 20 volts. Well, everywhere in my body is 10 volts. Everywhere in your body is 20 volts. If you had a very sensitive voltage sensor where you can sense points in the air from me to you, and you would see that if you touch my body, 10 volts, but if you're a little further away from my body, there's like a field here that's going to be 11 volts, and then 12 volts, 13 volts, until I get to your body, and if I touch that probe in your body, it'll eventually be 20 volts. But you don't want to disturb your experiment. That's why you would use this buffer here, this voltage follower. This copies the voltage, but doesn't disturb anything. Okay, here's the summing amplifier. Okay. The output voltage, I only have like 4 more minutes left, so I'm gonna just tell you guys how to do it without working the equations. It's the same thing that we used before. If I want to determine the output voltage, what I do here, I do KCL. Okay? I look at all the currents. Okay? The current going in there is 0. The current going around that way is that voltage minus that voltage over RF. The current going this direction, this voltage minus this voltage over R1. The current going in this direction is this voltage minus that voltage over R2. No current going that direction. The voltage here is copied from here, the non-inverting node. So it's grounded this particular time. I could have a source here. If that was 10 volts, that would be 10 volts. Okay, it just copied over. Once I have KCL, I plug in those values, and I'll have an equation that only has V out and VI, and I force it into a ratio, V out over VI. That's my gain. For resistance, again, this thing right here, since this is grounded, it looks like the only resistance you would see from this input is R1. The only resistance you would see from this input is R2, because it's going to ground right here. Going in this direction, you see no resistance because this path has low, super low resistance. So it looks like the resistance is 0 looking from the outside. Oh, and why is it a summing amp? Oh, the reason it's a summing amp is because V out looks something like this. It looks like RF over R1 times V1 plus RF over R2 V2. It looks like that. So if all your resistances were equal, there would be 1 and 1 here. So it just looks like V out is just like V1 plus V2. That's all. So that's why it's called a summing thing. And you go a little further. This is a summing amplifier, same thing, except it's summing several things. In this case, the thing that I'm summing here, I strategically made this with a base of 2. This is a digital to analog converter, binary, right? Where my input is 1 volt. These are on the ground, so that's either a 1 or a 0. These things right here are the bits. And it looks like this once you do it all, once you do all the math. Same thing that we did before, okay? But these are the bits. Here's the most significant bit. Here's the least significant bit. But these are the 1s and 0s. Those are the switches. Okay, so you plug in your 1s and 0s, and you get your result, going from digital to the analog domain. Okay? But same thing. If you want to do the math on this to get this, KCL. You have no current going this direction. You got this current, this voltage, minus that voltage over R. And then you got all of these currents, each one. But it's still KCL. It just has many terms. It has, 1, 2, 3, 4, 5, 6, 7 terms, but all KCL. And then you can get your this right here. Okay, so this is a difference amplifier, and to analyze this for V out, you do KCL right here, current, current, current. You also do KCL right here, current, current, current. You have this constraint where whatever voltage is right here gets copied over to here. So that's how you join those 2 KCL equations together. Okay? And then you solve it. Once you solve it, you'll end up with an equation that looks like this. It looks like V out equals something like, what was that? Don't quote me on this. But it's like RF over R1, V1 minus RF over R2, V2. Something like that. This whole thing may be multiplied by negative, but it's something like that. Basically, is looking at the difference between these two guys. I would have to do KCL to make sure the signs are right, okay? But you end up with a difference between the two, okay? Don't get this confused with a differential op amp. Okay, this is not a differential op amp. This is a difference op amp. We're looking at the difference between 2 inputs. And the last thing, real quickly, we're going to talk about more of this next lecture, but basically we're going to look at this frequency type of dependence of these op amps, where instead of calling these resistors, we're going to look at these as impedances. And these can be all kinds of things. You're going to have resistors and capacitors in here, same thing. And then same kind of analysis. Everything that we did before, it applies here. You just replace the resistors, the R values, with the Z's. That's the only difference. But they're complex and they have their frequency components like magnitude and phase. Okay, so that's it for today. See you guys Monday. Have a good weekend.